All right, any questions? There's a question about mercury. Mercury has two common oxidation states. There's mercury 1, which is Hg2 2+, and then there's mercury 2, which is just Hg2+. And so there are two common oxidation states for mercury.
Oh, so it's not the one?
I'm sorry?
It's 2+. What's it?
The mercury is a diatomic. This one's a diatomic cation. There's actually two mercuries covalently bonded to each other.
Oh, so that's why I have 2, but it can oxidation stay
Right.
with 1.
And so here, this is an ion, but you know, each one of these is a plus, and the whole charge on this is a 2+.
Oh, okay. Thank you.
Sure. So it's just unusual kind of. Okay, other questions?
What is the activity of aqueous? Like on the test, the question on the test.
What is the activity of an aqueous solution?
Yeah.
It's real concentration.
Real concentration.
Yeah, real. Real meaning
Effective.
effective, right? Because you know, ideal gas. The exact same thing happens with ideal gas. Ideal gas, you make some assumptions that there are no intermolecular forces. There's no particle volume. You know, and so when you calculate the pressures for an ideal gas is not for real gas, right? Is there such thing as an ideal gas that exists in nature? No. No. Is there really such a thing as an ideal solution that exists in nature? No, but all solutions approach ideal behavior at infinite dilution. You know, these are things you can see. I was talking to the afternoon class about the table. You know the table in chapter 13 we looked at briefly? The table is sodium chloride. Sodium chloride has a molality of 1.7, 1.8, 1.9. You know, at infinite dilution, it has a molality of 2, meaning that it splits up into two particles at infinite dilution. So, you know, the patterns there, you don't memorize the table, but you should memorize the pattern. There are 3 patterns in that table. One, you know, what happens at concentration? You know, the higher the concentration, the more ideal or the less ideal? 2, when do solutions approach ideal behavior? At infinite dilution. And 3, what does the magnitude of charge have? What impact does it have on ideal versus non-ideal behavior? The smaller the charge, the more ideal it behaves. The larger the charge, the less ideal it behaves. And so those are the 3 things that you summarize when you look at the chart. Now, you know, normally what people do is they just tell you, okay, memorize this, memorize that, memorize this. You know, but you know, what you have to do is you have to get used to doing this because that's what science is all about. You have a bunch of data and you got to what you call data reduction. Have you ever heard the term data reduction? You got tons and tons of data. What does all mean, right? And so you need to reduce it into more comprehensible things. And reducing into more comprehensible things is just simply looking for patterns. And so you spend a lot of your time looking for these patterns. That way you can take this enormous quantity of data and reduce it down into something that's more meaningful. Now the problem is that whole data reduction part is usually done for you, and you're told to memorize this, memorize that, memorize that. But the disadvantage of that is you don't see the original data. You know, it's better, it's nicer if you see the original data and you can come up with your own conclusions, right? And so rather, it's like the news. You know, when you hear the news, it's somebody else's interpretation of what all that means. You know, and you listen to the news, there's a lot of opinion in the news, right? And that whether you agree with it or not, you know, well, it's nice to have the original data so you can formulate your own, you know, analysis of what actually happened, right? Rather than taking somebody else's. But in science, the good thing about science is everything's peer reviewed. In news, it's not peer reviewed, right? News is it's just spit out whoever decides to write it. But in science, somebody spits out a bit of news, everybody's going to be critical of that. And they're critical in a good sense. They want to make sure whatever comes out is accurate. Right? That's sometimes science and politics get mixed up, you know, and that isn't always so good, you know, because usually things are, at least the data is presented in a way that's not really up for a review process. All right, what else? Any other questions?
So would that mean that on the, you asked which was more ideal solution, Na plus or Mg2 plus, or I don't know about whether it was which was more ideal or which was less ideal.
Which deviates more from ideal behavior?
Yeah, so it was which was less ideal.
Yeah, which one would be less ideal?
Mg2
Mg2 plus, right? Mg2 plus. Why? The higher the charge means it's like, okay, the exact same question comes up when in the gases chapter 6. Which one is a more ideal gas? Neon or xenon? Which one is more ideal, neon or xenon? Neon's more ideal. Xenon's less ideal. And so xenon, you'd expect greater deviations if you were to use the ideal gas law than neon. Both are pretty ideal though. You know. But neon should be better. Why? It has weaker dispersion forces. And so the same thing happens with solutions. Solutions and gases, the same thing. You know, trying to get that point across, thinking about this kind of stuff. You know, we tend to idealize things because, you know, it makes life easier. You know, when you have one equation fits all gases, it's kind of nice, right? One equation fits all. It's like a hat. You buy a hat, you don't have to worry because one size fits all, right? Maybe it's not the perfect fit, but it's close enough. Well, maybe the ideal gas law is not the perfect calculation, but maybe it's close enough. And so it depends. If you buy one size fits all, you put it on a small child, well, it's going to be a bad fit, right? Because that one size fits all is probably for adult. And so then you go, okay, the child, well, that's deviating farther from the ideal that hat was designed for. And the same thing with the ideal gas law. Ideal gas law is one size fits all, but if you were to use the ideal gas law for calculating steam, you'd expect quite significant deviations because steam has very strong intermolecular forces, right? Hydrogen bonding interactions. And so that's the problem with one size fits all. Therefore, we have fitted caps, right? Just like we have a real gas law. The real gas law, you have to use a different equation for each gas. So hydrogen has a different AB, helium has a different AB. You know, this is a different equation, totally different equation. Right? So, since we're doing one size fits all, at least you should have some idea where our calculations are going to be more accurate and where they're going to be less accurate, because we're doing all these equilibrium calculations using ideal concentrations, right? And so you don't want to treat every calculation the same. Or you don't treat every calculation the same. You treat them differently because you should have a sense for what the numbers mean. You know? So for example, if you get if you're looking at, let's say, 1 molar sodium chloride versus 1 molar magnesium sulfate, there's a difference. There's a difference. Well, anyway, so the thing is, you know, the people who can just do the math, you know, who can plug in the numbers, well, I know how to solve the quadratic. It's easy, right? Solve the quadratic. Right? That's not, is that real science? No, because anybody can do that without or with a science background. The difficult thing is analyzing what the numbers mean. Now, this is why the discussion section is very long in scientific papers. The discussion is analyzing what all those numbers mean, interpreting the news or whatever, what you're getting. And coming up with a sound argument so that if it's attacked by any way, you got to make sure it's solid, because people are going to look for holes in your reasoning. And then it should be published. There was sometimes there's different kinds of publications. There's something called a communication, which are not peer reviewed. Communications are things that have an urgent, that could be quite beneficial to other people. And so the peer review process in science takes a long time. After you finish writing a paper, you send it out to referees. The referees carefully read the paper and then write comments looking for any kinds of holes in your analysis. And that usually takes 1, 2, 3 months, because the referees are quite busy. The referees are just like everybody else. They're just people working just like you. And when you get into science, you're asked to referee papers also. It's part of the job. And so, you go through and the peer review process, and that prevents things. But sometimes certain things slip through, that maybe weren't sent to the right referees. Those certain referees aren't quite as familiar with the field as others. So one of the things that, Nature there's some premier journals like Nature, Science. Those have very strict referees, but sometimes things slip through and are retracted. One of the things that slipped through and was kind of retracted, but not officially, is this thing about arsenic-based life forms in Mono Lake, the arsenic bacteria. It turned out to be a contamination issue. And then not only that, sometimes papers are published and other people look at their data and come up with a totally different interpretation. And so this is why in scientific papers there's something called results and discussion. Results are just your observations. Observations are fact, because there's no analysis. It's like if you were to get the news directly from the source, right? And just observe what's happening. The discussion is the analysis of those facts. And so typically in a paper we have results separated from the discussion. We want to separate the facts from your analysis, because your analysis could be wrong. And so there are a whole bunch of papers in the literature saying reinterpretation of so-and-so's data, because they didn't like their analysis at all, and so they published a second paper using their data, the results, and coming up with a different analysis or different discussion. And that happens frequently. Also, technology changes too, because sometimes that happens rapidly. Sometimes new instruments come, and or new theory comes along to better understand this. And so the hard part of this is it's not being able to. I know a lot of people who think this science is just being able to punch it into their calculator and that's it. Well, I've been watching documentaries about outsourcing and this kind of stuff. That type of stuff, punching in the calculator can be easily outsourced, right? That type of stuff is not a special skill. That doesn't make you a scientist. What's going to make you a scientist is being able to do the harder stuff. What's the harder stuff? The harder stuff is to analyze, to have some idea of what the numbers mean, that are spit out of there. For example, xenon versus neon. And then even deeper than that, because when you look at the ideal gas law versus the real gas law, the two things that deviate can self-cancel each other. One tends to lower the pressure, the other tends to increase the pressure. At some point they self-cancel each other. but it tends to minimize the deviation for certain things. And so that's another reason the ideal gas law gives its fairly decent results until it starts to skyrocket away from there. So all these questions about, magnesium versus sodium is just to give you an idea that they aren't the same. All right, what else? That's it? Okay, we need to move on. I need to finish up chapter 16. Where did we stop for chapter 16? Polyprotic acids? Polybasic bases? Did we start a polybasic base yet?
Yeah.
Okay, where did we stop on the polybasic base?
Phosphate.
Okay, did we do step 1? Step I? Did I do step I?
Yeah.
We did a step 1?
No, actually.
Okay, let's just go ahead and, did we do step 2?
We started.
Okay, we started step 2, but at the end of step 1, we had the choice, because step 1 is, this phosphate hydrolyzes water to produce monohydrogen phosphate and hydroxide. This is a KB. We calculated KB, right? For this one. This is also called KB1 for phosphate. And so initial change, equilibrium. Can you tell me what the equilibrium values were? 0.0617 molar. Water is a liquid. HPO4 minus 383, and hydroxide 0.0383 molar. All right, now we have to figure out what we're going to do next, because we did phosphate. Well, we're left with monohydrogen phosphate. Now, monohydrogen phosphate is, did I talk about this? Is amphoteric. And so amphoteric species can collide with water and lose a proton, or it can collide with water and, did we already do this? No? This is where we're starting? All right, the situation with monohydrogen phosphate is it can collide with a water molecule in 2 ways. One, it collides and it gains a proton. HPO2PO4 minus plus a hydroxide. Or it could collide with water and lose a proton to form PO4 3 minus plus hydronium. And so once we form HPO4 minus, it could either lose a proton or gain a proton, or which one does it do? Mm-hmm. Yes, HPO4 2 minus. Which one it does? Well, let's see. This one up here, if it collides with water to gain a proton, then it's acting as a base. So this is what we call a KB, base hydrolysis, base plus water. Right? And so what is the KB for HPO4 2 minus? The KB for HPO4 2 minus is AKA KB2 for phosphate. And so this is, the second, picking up the second proton, which is equal to what? Which is equal to KW over KA for what acid? H2PO4 minus. Which is equal to, well, the Ka for H2PO4 minus, Kw is 1.0 times 10 to the minus 14. Ka for H2PO4 minus is 6.3 times 10 to the negative 8, which gives me a KB of
1.5.
okay, 1.5 what? Give me-
8.
8. 1.58 times 10 to the negative 7. All right, what is the Ka, because this is acid hydrolysis, all right? Here are amphoterics acting as the acid donating proton. And so what is the Ka for HPO4 2 minus?
4.2 times 10 to the -30.
Do both of these happen? Do both of these collisions happen? Yes. Both of these collisions happen, but which one's more favorable? Is the KV collision more favorable, or is the KA collision more favorable? The KV collision is more favorable. Do you see that? Why? The number is a lot bigger. And so this one looks to be favorable, right? So let's go on to step 2. Phosphate's a tribasic base, so it has the potential for picking up 3 protons. And so we'll go with monohydrogen phosphate, where we left off from step 1. This goes down here. And this is going to collide with water. And the collision that looks more favorable is the Kb collision, so it goes to H2PO4 minus plus hydroxide here. And so we'll plug in the numbers here from step. This should be 0.038. From step 1, we have 0.0383 molar initial. Water is a liquid. H2PO4 minus. How much initial?
0.
How much hydroxide initial? A lot of people say 0, but that's not really true.
Yeah.
Because we have hydroxide from step 1. That's 0.0383 molar. And so then we're going to have a change. This is going to be minus X. This is going to be plus X. Plus X. So at equilibrium, 0.0383 minus X. X molar. And 0.0383 plus X. We know our Kb value for this. Let's go here. Our Kb value was 1.58 times 10 to the minus 7, which is going to equal the H2PO4 minus times the hydroxide, and divided by the HPO4 2 minus. So this is going to be X times 0.0383 plus X over 0.0383 minus X. So just a quadratic. So we could either solve the quadratic or we could try what? We could try the simplifying assumption. Usually I just go ahead and try it, because it's easy. I go ahead and try it, and then the X drops out here and the X drops out there. And then if we use the SA, then X is equal to Kb, 1.58 times 10 to the minus 7, which is K. We calculate the percent change. Percent change is going to be the change X over the initial 0.038, and it comes out to what? Very small. You see, it's going to be very small because it's like 10 to the minus 7 divided by 10 to the minus 2, which is going to give you about 10 to the positive, oh wait, no, 10 to the minus 7 divided by 10 to the minus 2, which gives you 10 to the minus 5. And so it's roughly a 10 to the minus 5% change, somewhere around there. 10 to the minus 4, 10 to the minus 5, 10 to the minus 6% change, which is very small. Oh, so what do you think about the simplifying assumption? It works great. Does it work great? Why does it work great here? Is it because of the KB? Why would you think it would work great in this case?
Because not much product is going to form.
Not much product is going to form? Why?
Because it has a really small KB.
Okay, it has a pretty small KB, that's 1 plus. And so would you use that as a rule? If you have a 10 to the minus 7 K, then the simplifying assumption works?
Because the initial is so small too. So
The initial's kind of small, so maybe it wouldn't work, right? The initial being small hurts you. And so why do you expect it to work in this case especially well? Do you see it work especially well here? Is it just based on the K alone, or is there another factor?
KB is that much smaller than the initial molarity.
Okay, I guess we could come up with a KB to initial molarity ratio, but it fails. The KB to initial molarity ratio or the initial molarity to K ratio fails because this is different. They give you the guideline K over initial or initial over K, but that's only if you have. There's another factor that makes this especially good. What's the other factor? Somebody explain it to me.
It's the phosphate is weaker base and the hydroxide.
That's not the reason. This is way better than you would expect based on the ratio. Why? This is way better than you would expect based on the ratio. If we did the ratio K to initial or initial over K, this works much better than the ones we would have seen earlier. Because I'll tell you, even with a 10 to the minus 14 K, sometimes we have to use the quadratic. Don't you remember that? If K was 10 to the minus 14, which is 7 orders of magnitude smaller, sometimes we have to use the quadratic. Why did it work so well in this case with only a 10 to the minus 7 K value?
Percent hydrolysis. And
The percent hydrolysis for step 2 is incredibly small. The reason is, why? Why is the percent hydrolysis incredibly small for step 2? Actually, we could calculate the number. Let me calculate the number. So the change was 1.58 times 10 to the minus 7 divided by the initial 0.08383 times 100. 4.12 times 10 to the minus 4% hydrolysis. Very small number. Even before I did the simplifying assumption, I knew it was going to work great in this problem. Why? Not because of the K value necessarily, but it was a combination of K and what? I knew X was going to be extremely small in this case because we're not quite ready for chapter 17 yet because you don't see it.
The initial values
Hmm? It has something to do with initial value, but it's not the initial values are the same. Come up with a better. We're not quite ready for the next level of calc until you can see this right off. This is the first calculation we do in chapter 17. One of the first.
Is it the initial hydroxide?
Yes. It's because of the initial hydroxide. Now, how do you explain that? Can you explain it to me?
If it goes beyond a certain concentration, the solution will be saturated with hydroxide.
No. No, I could add so much more hydroxide. It's not even close to being saturated.
Concentration of hydroxide is so high, so the water, the hydroxide from water will be very tiny.
No. We haven't even gotten to water yet. We're just looking at step 2. This is something I've been trying to get you thinking about so that you're ready for chapter 17, the first calculation, type of calculation we do in chapter 17, but you haven't done it yet. You either use my story and recognize my story or interpretation of it, or you do your own. It's better to do your own because if you listen to somebody else's, it's not as meaningful, you know. And maybe it just doesn't agree with your senses, you know. And so you come up with your own. Okay, that would be what we call Le Chatelier's what? Well, I called it something else. Or you could use some other analogy for this. What was the analogy I used in class for this? Huh? Right. So, Adrian, why don't you tell me more? See, if you don't understand this, then you aren't going to understand the first calculation in chapter 17. What was the whole thing? If you don't like predator and prey, then come up with your own, you know? Your own little thing.
Isn't it the hydroxide is like the predator, so whenever the hydrogen phosphate forms, it'll attack it to go back to...
Right. And so that's one way of visualizing this. The other way of visualizing this is Le Chatelier's principle in action, but we don't call it... Can you shift it to the left? Can we shift this to the left? No, the only way we can go is right. But normally if you have a lot of excess product here, you want to shift left, but what this excess product does is it inhibits the shift to the right. So we don't call it Le Chatelier's shift, we call it Le Chatelier's like inhibition for the forward reaction because it's going to prevent as much. If this were both 0 and 0, right? If both of these were 0 and 0, it's a different story altogether because 0, 0, you expect it, no problem, you know, to equilibrate. But already when I saw this, I knew X is going to be really small. Really small. Because this is small and we got a lot of product there already to begin with.
Is it also because the more protons that the phosphate accepts, the more stronger acid?
No. That doesn't have any, because this could be 0 to 0 and accept more proton. Dihydrogen, you'll form more dihydrogen phosphate. If this were 0 and 0, this would be a much higher concentration. But this type of problem in chapter 17 is called the common ion problem, and that effect is called the common ion effect. And a common ion problem, common ion effect. Basically, that's it. You know. Common ion problems are very common with these ice tables because we mix different things together in here. But anyway, let's continue with this. We see the SA is really good. No problem. If you did the quadratic, there's no reason to do the quadratic when your SA is that good, you know, because you'll get the same number. And so let's go ahead and do the calculations here. Actually, let me do it up here so I have room. So the equilibrium calculation would be 0.0383 minus x. X, I need 6 zeros and 158. 1, 2, 3, 4, 5, 6, 1, 5, 8. I need to add some extra zeros here. It's going to give me 2, 4, 8, 9, 9, 2, 8, 3, 0, 0. And so did I lose much? You know, I went from 383 to 382, 998, 42. Barely lost any. Molar. For the dihydrogen phosphate, I'm going to have this 1.58 times 10 to the minus 7 molar. For the hydroxide, I add a little bit. So the hydroxide is going to be 0.0383 plus 60158. So that's 0.0383000158. All right, now I want to double check these to see. Now I carried extra digits there. I carried extra digits because the change was so small. I didn't want to round it off. Because if you were to round this, what would this round to? 383. 383 or 38, you know. 38. It looks like nothing changed, but something did change. We lost a little bit. And if I were to round this, it'd just round to 383. Basically. It looks like I didn't gain any, but I actually did. It's just a tiny bit over here. And so, does this check out the K value? Let's check out the K for this. .58 is 10 to the minus 7 times 0.0383 00158 divided by point. I'm carrying extra digits to minimize round off error. 382994842 gives me a K value of 1.5800 times 10 to the minus 7. Is that good? Yeah, that's good. But we have to ask ourselves this. After we complete step 2, we need to see, did step 2 perturb step 1's equilibrium? And so we did add some hydroxide here. Adding the additional hydroxide, is that going to mess up the previous step's equilibrium? No, because it's so small, the addition's negligible, it really doesn't change K significantly. And so there's insignificant. And so this does not perturb. If it does not perturb the previous step, then we could do this stepwise instead of doing it, what's the other choice? Simultaneous. And that means we can continue. Stepwise is a lot easier to solve than simultaneous. And so we're good. But what about the other collision? What was the other collision for monohydrogen phosphate? Yes. So let's take a look at the other collision. But what about the Ka collision? The Ka collision was HPO4 2 minus plus water is going to yield phosphate plus hydronium. And so aren't we generating some hydronium? If we generate hydronium, that's going to change the hydroxide, isn't it? So what about the Ka collision? Does the Ka collision happen?
Yes.
Yes. Can you stop the Ka or prevent the Ka collision from happening? No. And so do we have to do the ice for the Ka? We could say it's negligible and ignore it, but that's wrong, because then we should ignore Kw, right? And sometimes Kw. Why would you, I mean, in other words, if you were to say it's negligible, why would you say it's negligible?
Because the Ka is really small and there's a lot of phosphate initially.
Okay, so you're saying the Ka is really small?
And there's a lot of phosphate.
There's a lot of monohydrogen phosphate?
No, just phosphate.
Oh, a lot of phosphate. So you're saying the same thing, the predator and the prey. There is a lot of phosphate. You're right. Because when we look at the initial phosphate was 0.0617 molar. And the monohydrogen phosphate would be 0.038 molar. And the hydronium would be 0 molar. And so you would say that this is negligible because of the okay, the Chatelier's kind of inhibition, or because we have a lot of phosphate in there, which is product, or we're going to start calling it common ion because we have a lot of common ion there, which is going to prevent the forward reaction from occurring. Therefore, we expect this to occur negligibly. That's what you're saying, Keith? That's wrong. That's right. It's right that you'd expect it to occur negligibly, but it's wrong to say we could ignore it because it occurs negligibly. This is very tricky. This is very tricky because this describes the equilibrium between HPO4 2 minus and PO4 3 minus in terms of pH. What was step 1? Go back and look at step 1. And describe step 1 to me. What does step 1 tell us? The equilibrium between what and what? Yeah, step 1 describes the equilibrium between the same species, except in terms of OH minus instead of H3O plus. But do you know OH minus and H3O plus are connected? How are they connected? Because if the H3O plus goes up, the OH minus must go down, and vice versa. In other words, these are connected because pH plus POH has to equal PKW, which is 14.00 PKW. Now, so the reason we could ignore this is not because it's negligible. The reason we could ignore this is because we already did this. We already did this, but instead of representing the equilibrium in terms of pH, we represented the equilibrium in terms of pOH. And so this is redundant. We already did this. In other words, it's redundant to do it again because we're going to get the same number, except rather we'll get the hydronium instead of the hydroxide. So there's a lot of different collisions happening, right? And we have to be able to sort through the collisions to see, this is the same as the other one. Or this is unique, this is different, we have to do it. And so there's a rule that we're going to use. Therefore, this works. In fact, all the Kas that we're going to see are going to be redundant. And so for base solutions, only hydroxide contributors are considered. Because, hydroxide and hydronium are tied together. And so for base solutions, we only look at the Kb. This is a base solution. Phosphate's a tribasic base. And therefore, we're only going to be looking at Kbs. And so even though there are Kas, because we're dealing with amphoteric species, we ignore them. Kw is unusual because Kw is both a Ka and a Kb. And so we only look for hydroxide contributors. For acid solutions, we only look for hydronium. The other ones would just be going in circles. Does that make sense? And so what about the Ka? Well, we already did it, so we aren't going to worry about it. Or it's already factored in to play. And you get the same equilibrium. Collision's going to happen for sure, but the amounts are going to be already dictated by what we solved. And so the next step here is this. What we did was we generated some dihydrogen phosphate. Dihydrogen phosphate is amphoteric. It has both a Ka and a Kb value. Which collision are we going to look at? Only the Kb collision, right? This is a basic solution, therefore we only look for the... And because the Ka equation for this, just look, what would the Ka produce? Can you do this in your head? If this acted as the acid, what would it produce? It would produce monohydrogen phosphate and hydronium. Well, monohydrogen phosphate and dihydrogen phosphate, didn't we just solve that equilibrium? Yeah, we just did it. And so that would be redundant. And so what we're going to do is we're going to do the Kb for this. The Kb is going to give us H3PO4. This is unique because we haven't solved that. Have we solved the equilibrium between H2PO4 and H3? No. And hydroxide. This is the tribasic base can accept 3 protons. And so this is the final proton here to end up at H3PO4. And this is called Kb for H2PO4 minus, which is called Kb3 for phosphate. And Kb for H2PO4 minus is equal to Kw divided by Ka for what acid? H3PO4, its conjugate acid, which is 1.0 times 10 to the minus 14 divided by, what's the Ka for phosphoric acid?
7.5 times 10 to the negative 3.
Are you using this? Let's not use this. Let's use our book because
7.1.
7.1 times 10 to the minus 3. That data's old on that chart. I don't want to use that data. New data comes out, you know, things get more, technology advances, things get more accurate, precise. So the KV for this is 1.40 times 10 to the negative 12. We have to worry sometimes because, you know, when we do it stepwise, what order do we go? We go from the largest K to the smallest K. In other words, we go from the largest hydroxide contributor to the smallest hydroxide contributor. Sometimes with these triprotic, you know, let's say this were 1.4 times 10 to the minus 15. If this were 1.4 times 10 to the minus 15, would I go here? I wouldn't go here. You know where I'd go? 1.4 times 10 to the minus 15 is an awful small number. You expect much hydroxide from this? No. And so if this were 1.4 times 10 to the minus 15, I would not use this as my step 3. I would instead go to, what would give you more hydroxide? What would give you more hydroxide? Water. I would go to KW. Does that make sense? Because KW would be a better hydroxide contributor than this. And so I go from biggest to smallest and fit KW wherever it fits. And so there are some problems where, you know, this is a tribasic base, but KW gets in there before the third proton's accepted because it's not such a great base. Water turns out to be a better base. Does that make sense? And so it's kind of a trick question. A lot of people don't do that. They just look at KB1, KB2, KB3. They go in that order, KB1, KB2, KB3, because it seems to make sense. You know, you just go in sequence, but they're wrong because KW is a better contributor than KB3. Even KB2, there's some dibasic bases that are like that. Which I'm given on tests, past tests, and maybe about 10% of the class figures it out right. 90% gets it wrong, which isn't good. It's all right because don't expect everybody to get it. But in this case, would we go to KB3? Sorry, this is not KB2, this is KB3. Or would we go to KW? KB3. KB3 is bigger than KW, so this should be a better hydroxide contributor. And so let's go ahead and do this. What's my H2PO4? 1.58 times 10 to the negative 7. And that's from here. What's my H3PO4?
Yeah.
What's my hydroxide? Do you have to carry that many digits? No. Which way is this going to go? Forward. 4, minus x. Plus x. Plus x. So at equilibrium, I'm going to get 1.58 times 10 to the minus 7 minus x. Molar x molar. 0.038300158 plus x. What do you think about the simplifying assumption? It should work Well, anyway, Kb, this is going to equal the phosphoric acid times the hydroxide divided by the dihydrogen phosphate, which is going to equal x times 0.0383 dot 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 plus x divided by 1.58 times 10 to the minus 7 minus x. What do you think? Works great?
Yeah.
Well, over here, I'd expect x to, for sure here, I'd expect x to be negligible, right? To drop it out. But here, I would start to worry. Why?
That's what equals.
Because the initial is so small. And so this would be more advanced. You know, you could do a partial simplifying assumption. That is, you can make the simplifying assumption for the numerator, but for the denominator, maybe just keep it. And it simplifies the math, so it's not quadratic, linear equation. That's one thing you could do, or just do it for both. If we do it for both, let's see what we get. And so let's calculate x. I'm just going to go ahead and use the simplifying assumption because it's just such a quick calculation. It doesn't take much time to do. We can check it right away. So we got 1.4 times 10 to the minus 12 times 1.58 times 10 to the minus 7 divided by 0.0383. If you want to add the rest, 0.00158. What do you get? X equals 5.7. Yeah. Okay, I got 5.77. I carried some extra digits. Times 10 to the negative 18. Did it work? Yeah. No problem. It worked fine. So, 10 to the minus 18, is that really going to have an impact here? I don't want to write 17 zeros, actually. And so this is going to be about a little bit greater than 1.58 times 10 to the minus 7 molar. This one, can I ignore it and just call it 0? No. This one's going to be 5.77 times 10 to the minus 18 molar. And this one is going to be slightly above, and we'll just call it 0.0383 molar, roughly, slightly greater than. Did step 3 perturb step 2? If it doesn't change between step 2 and step 3, why am I doing step 3? Yeah, we need to find out how much H3PO4 there is. So now we have it. Why would I do step 4? Why would I bother even doing step 4? It's likely not going to perturb. It's because I want to figure out how much. Not OH minus, because step 4, do you think it's going to contribute much OH minus? K is even smaller, but it will contribute hydronium. So the only reason I do step 4 is to figure out how much hydronium. In fact, if I only cared about my pH, and I can calculate pH from POH. So if I only cared about POH, what step should I have stopped at? Did step 2 contribute a significant amount of hydroxide to step 1? No, I would have stopped at step 1. If all I cared about was the pH of sodium phosphate, I could have done it in one step, step 1. because the remaining steps really don't contribute much. And so for most weak acids and weak bases that are polyprotic or polybasic, step 1 is enough to get the pH. You know? There's some acids where you would have to do step 2. For example, sulfuric acid. Sulfuric acid is a diprotic acid, you know, and about 90% of the hydronium comes from step 1 and about 10% comes from step 2. But for phosphoric acid, you know, 99.9% comes from step 1, and so little comes from step 2 we ignore. And so for pH, Petrucci has this thing, you know, where you just do step 1 for most. We don't have to do this. The only reason we're doing all these steps is to get the proper inventory for this. And there's only one last species, this is the hydronium, so let's go ahead and figure that out in step 4. Step 4, let's see how much H2O contributes to hydroxide. Remember, we're looking at just the hydroxide ion contributors. And so Kw we're considering as another Kb, because Kb is contributing hydroxide. We just want to know how much of this species is also being generated. And so we'll go with initial. How much initial hydronium? 0. How much hydroxide? 0.383 ... molar. Change is plus x. Equilibrium, I'm going to have x molar and 0.0383 ... plus x molar. Kw is hydronium times hydroxide, which is going to just be x times 0.0383 ... plus x. You think the simplifying assumption will work? Yes. Sure. Should work good. So this is just going to be the SA, and x is going to equal I'm not going to carry out all those digits. What do you get?
3.6.
3.6 times
10 to the negative
10 to the negative 13. 3.6 what?
13.
3.65. Is that what you guys got? 2.6? 2.6 what? 2.61? Okay, it sounds like most people do that. This is kind of weird because this one actually contributed more hydroxide than the, but we didn't carry out all the digits. Well, anyway, is that going to make any impact really on the hydroxide? 10 to the minus 13? That's way out here. It really doesn't make any impact on this. It doesn't perturb it. But over here it does, you know, and so 2.61 times 10 to the minus 13 molar and 0.383 ... molar. And so let's figure out what's in this beaker now. If I have a beaker that is 0.100 molar sodium phosphate, what are all the species I'm going to find in solution and their concentrations, starting with the most abundant species? What's the most abundant species? Yeah, 0.300 molar sodium ion. Okay. What's the next most abundant species? Hydroxide. 0.0383 molar hydroxide.
Oh, we move on phosphate.
Phosphate, point
0.06.
Okay, followed by hydroxide. How much hydroxide? Here, 0. A little more than 0.383 molar hydroxide. Followed by I'll carry an extra digit because this is closer to 3 than 2.9 molar. Followed by H2PO4 minus, how much? 1.18, did you say? 1.58. 1.58 times 10 to the minus 7 molar. Next. Hydronium. Okay. 2.61 times 10 to the minus 13 molar hydronium. And phosphate or phosphoric acid. What is it? 5.77 times 10 to the minus 18 molar phosphoric acid. Is that it?
Water.
No, water. All right, there's two ways we could get the pH. We could get the pH from the hydronium, or we could get the pH from the hydroxide. If we get the pH from the hydroxide, we go just POH to pH. They should give us the same number, right? So what is the POH? It's a negative log of this. What is it? 1.41, which means the pH, well actually give me one more digit because we're allowed two. 1.416. And so the pH is equal to 12.584. All right, now let's calculate the pH based on the hydronium, just straight. What does it come out to? It better come out the same, otherwise I think it's wrong. 12.583. What's the difference here attributed to? Are these the same number?
I got 12.583 for the pH if you carry more digits.
Oh, if you carry, all right. Yeah, these are both the same number, it's just the difference is the round off error, that's all. And so it's checked out, okay. And so what, when you go back through and do this problem yourself and then review it, certain things you can see, why do you do all these steps to get the total inventory? If you wanted pH, would you have to do all these steps? No. A lot of calculations, all they ask for is the pH. You could save a lot of time. All right, then why don't you do this calculation at home? So this calculation would be 0.100 molar H3PO4. Rather than starting off with the base, sodium phosphate, we start off with the acid, phosphoric acid. When we're dealing with phosphoric acid, we got Ka1, Ka2, Ka3, and Kw. If we only wanted the pH, which one do you think we'd do? Ka1, maybe Ka2. It depends on how big. We would have to worry about Ka2 in general if it's kind of high or kind of big in magnitude. And so let's take a look at just the chart values over here and see if we see something here. If we look at phosphoric acid, Ka1 is 10 to the minus 3 weak acid. Ka2 is 10 to the minus 8. 10 to the minus 3 to 10 to the minus 8, that's 5 orders of magnitude, roughly. Which means Ka2, would you expect it to contribute much additional hydronium? No. All right, now for pH, I'd probably just do step 1, Ka1. It certainly wouldn't do Kw. But it also depends on the concentration as well. Now for sulfuric acid, we do Ka1 and Ka2. When you look at sulfuric acid, the Ka1 is very large. For sure that's going to be a big contributor. So take a look at Ka2. Ka2 is 1.2 times 10 to the minus 2. Now that's like 0.012. 0.012 is going to be a significant contributor because K is kind of big. And so when you have something like 10 to the minus 2 versus 10 to the minus 8, 10 to the minus 2 is going to yield a lot more hydronium. And so it turns out with numbers like this, 90% of the hydronium comes from Ka1, and about 10% of the hydronium, 11% comes from Ka2. And so when you see pretty large Ka2 values, like 10 to the minus 2, which is not considered large, then step 2 should be a significant contributor. But if you see a pretty small K value for step 2, then it's not going to be that significant of a contributor. And so you have some similar problems. All right, what we've been doing in chapter 17 is trying to keep it simple. That is, you either look at just an acid solution or a base solution. Just an acid in water or base in water. In chapter 17, we're going to look at more complicated mixtures. And so chapter 17 is what we're doing next here, which is acids bases part 2. And so we're going to have more than just some phosphoric acid in water. We're going to have phosphoric acid and something else in water. And so let's take a look at some of the mixtures that we can have. Actually, in chapter 16 we were looking at mixtures too, but the mixture was just this plus water. Now we're going to be looking at mixtures which are a bit more complicated. And so, mixtures would be like this. Mixtures would be like a strong acid plus a strong base. Strong acid plus a strong base. So we would have something like HCl plus sodium hydroxide. What do we get for this? Well, you know what we get for this. Sodium chloride and water. Is this a Ka or Kb? No, neither. This is a K reaction. Ka is acid plus water. Kb is base plus water. This is K for whatever, neutralization. Do you know this number? You should. What is the K value for this? I call the K for this, I call this K very, very, very large. This is very, very, very large. Why? Because I have some reference points for this. The reference points I have for this would be like this. HCl plus sodium hydroxide. Sodium hydroxide is a strong base, right? Hydroxide is. What's a weak base? NH3, let's take NH3. NH3 would give us something like ammonium chloride. You know what I call K for this reaction? I call this one very, very large. I call this one very, very large. That's because of this. What am I comparing it to? I'm comparing it to water. Is water more basic or less basic than ammonia? Much less. Ammonia is a much more powerful base than water. And we already know strong acid plus water, what is this going to give us? This is going to give us hydronium and chloride, and I know what the K for this is. This is called Ka. Ka for this is very large. So if I'm taking a strong acid and reacting with water, which is not a good base, and I still get very large, then this has got to be even larger, and this has got to be the largest. And so this is how we get the scale, or how I got the scale for this. The scale is and so what we say is strong goes to completion. Strong goes to completion because the K should be big. Yeah. Strong go to completion. So let's look at a strong base. Give me a strong base. Let's not use hydroxide. The hydroxide's overused. Let's use one of the underused strong bases. Huh? Amide? Yeah, let's go with amide. Sodium amide I call step I. You remember that? Step I? What was step I all about? Is sodium amide a strong base? A lot of people say sodium amide is a strong base, so it ionizes 100% into sodium ions and amide ions. Is that true or false? Sodium amide is a strong base, therefore it ionizes 100% into sodium ions and amide ions. True or false? That's false. Yeah, that's false. And so this is why I call this step I. Step I, this is sodium amide is what we call a strong electrolyte. It's a strong electrolyte because it's a strong base? No. Strong acid? Soluble salt.
Wait, so it's not a strong base?
It is a strong base, but the strong base is not sodium amide. The strong base is amide. And so here we have our strong base.
We have a strong base with that. Make it ionize completely.
Okay, ionize amide completely. Amide's a strong base, so ionize it completely. I give this on tests. People ionize this completely. They ionize it into N2 minus or N3 minus plus H minus plus H minus. They come up with the most bizarre stuff to break it apart. And then I got tired of reading those So I thought I better change this a little bit because I don't want people to ionize. Amide. Amide doesn't ionize. Yeah, amide hydrolyzes. So this ionizes.
That's what I was trying to say.
And so people think, oh, strong base, sodium amide is a strong base, it ionizes. And then I give them amide, tell them it's a strong base, and then they try to ionize it. So, strong base plus strong acid. What's a strong acid? Give me a strong acid. Nitric acid, all right. Nitric acid is always a dangerous acid. Why? Is it because nitric acid is stronger than hydrochloric acid? Yeah, in fact, it looks like hydrochloric acid is a stronger acid than nitric acid, doesn't it? In water, they're the same leveling effect. No, it's because it's an oxidizing acid. Texas is a state that has a lot of problems with nitrate. You know, I was looking at. Actually, we don't have much time, do we? I was looking at just the magazine yesterday, and they came up with a report. There was a explosion there that destroyed a middle school and a apartment complex and killed 15 people and something like this. But anyway, going back to this, amide plus a strong acid like nitric acid will give us what? Ammonia plus nitrate. What is K for this reaction? All right, strong plus strong acid? Yes. Okay, let's go with weak acid. Give me a weak acid. Yeah. A weak acid like acetic acid, which I'm going to use the abbreviation HAC for acetic acid, gives us ammonia and acetate. K for this reaction should be large. And then let's go with water. Water, what's a stronger acid, acetic acid or water? Acetic acid. And so when a strong base like amide reacts with water, what's formed? Ammonia and hydroxide. And K for this, which we call KB, is very large. So these acid-base reactions just go to completion. You know, we have this acid-base neutralization, and we figure out what's left over. These are called titration. Titration reactions. Now we'll stop here. We're going to continue looking at these.